Before starting the question, so how many of you are familiar with machine learning, at least in a non-technical way? You all know what machine learning is, supervised learning and unsupervised learning, how it works. Okay. So, I can skip what is supervised learning. Given a data, you have data in the labels, and then you trying to learn a function that maps from x to y. And similarly, another category called unsupervised learning, where you given the data, you try to learn the pattern out of it. It might be how many number of clusters are there, how the data is grouped into various categories. So when we talk about generative AI, so given a input data, and your model is that function that you are trying to learn, and y is your output. X could be number of features that you are giving it. For example, let's say in a email classification problem, whenever you receive an email on your Gmail account, you might see it either goes to primary or social or update or promotions. There are categories. So that y could be a label, that categories you have, or it could be a probability value or a number in case of regression task, right? Till this point of time, I think you all are familiar with it. When we talk about generative AI, we want to generate content. So that the content might be a text which you are getting in a natural language. It could be image, it could be audio, or it could be video. So if we talk about generative versus the model that you have studied in machine learning called discriminative model. So given some data in form of whether a structure or unstructured data, you are trying to find out a category or number. So those are the models are called the discriminative models. In turn, generative models where you are trying to generate new data, and to simplify it, given a data, how you are going to generate new data out of it. So one of the easiest ways to learn the probability distribution of the data. So once you can learn the distribution of the data, you can generate new samples. So unlike discriminative models where you are using conditional probability to learn a category, now we are trying to learn the distribution of the data. So that definition you might have heard in the previous session as well. That also known as a density estimation. When you try to learn the probability distribution of the data, you can think of it as a problem of learning as a density estimation as well. So how it works basically? So how we can say we have a generative AI model or generative model basically. So to understand it, consider a simple example. So let's say when we are talking about learning a probability distribution, you have some numbers. So we are simplifying and taking a simplest example. Suppose we have some numbers, and when we say we want to generate new numbers which are similar to this, when we say similar to this means what? That follows the same distribution which this data is following. So how you can define similarity? So how you can define which numbers are similar to this?
Find the mean and standard deviation.
Find the mean and standard deviation. This could be this is one of the ideas. So you come up with a mean and standard deviation of the data. Once you have the mean and standard deviation of that data, you can easily generate new data. So assuming you have mean 5.0 and standard deviation 1.2 for this particular data, and once you got those two values, you can generate a new samples as well. So assuming this follows a normal distribution, focus on this, and we get a new sample. You just pick a sample from it and multiply with the standard deviation and add with the mean, you will get the new value. And we can say this new value will be following the same distribution. So let's say new value is 5.495, round figure 5.5, same distribution which this data have. So we got new data based on by learning the probability distribution of the training samples or the data that we have. And you can generate more data by taking new value for z from normal distribution, and you can generate some more data. So we can say this new data is similar to the data that we had initially. So this is the idea of generating new data out of given some training data. Yahan tak clear? It is clear at this point of time? The problem is, so why we cannot use that same approach in the real world? Why not just get the data and just learn the probability distribution, just get the mean and standard deviation of the data and just generate new samples? So there are many problems. Real world data like text, images, videos are basically do not follow the simple distribution like normal. They are more complex in nature. Like images have, even in your mobile, normal images have a size of 1024 into 1024. So you cannot just learn the probability distribution simply by assuming it is a normal distribution of person. The second problem is it is high dimensional in nature. Even a smallest picture or smallest video have high dimensional data. So you cannot assume it only follows a single distribution in the data. Even let's say you have a data of two type of images, cat and dog. So cat might be following some other distribution, dog data might be following other distribution, and even let's say you have a structured data where you have number of features. Structured data means in a row column manner where you have features f1, f2, f3, f4 and so on, and each row represent one data, for example x1, x2, or d1, d2, d3 and so on. So each feature might be following some different distribution. So you might have multi-model distribution of data. So you cannot just simply calculate mean and standard deviation to generate new data. Also, so okay. So multimodality is a problem, diversity is a problem. So you cannot just simply come up with a probability distribution to get a sample out of it. So how researchers have started? So now we understood that we need to learn the probability distribution of the data. So they started with so all the research that has been done. They categorize all the models into two categories: explicit density estimation and implicit density estimation. So by these two categories, earlier researchers thought, okay, so let's define a probability distribution function for complex data and then learn over it. So how we can define probability distribution for, let's say, text or images? So one of the ways you can define an image as a, so let's say this X is your image. Then the probability distribution of image, we can think of a product of all the pixel values. So that xi is basically belongs to that x. So if you have an image, why not we can define conditional probability as a probability of particular pixel given some previous pixel. And why not multiply all those probabilities over all the pixels? Suppose you have n pixels, you can define the probability distribution of a image as a conditional probability of each pixel and multiply it, and that will represent the probability distribution of one particular image. What about text? So for text you can define given a text, for example, I like this course. You can define the probability distribution of this whole sentence as a joint probability of P of I multiply with P of like given I multiply with P of this given I and like and so on. So this is, we are decomposing a sentence into a conditional probability of each word. So starting with probability of I given previous, which is not there, probability of like given I and so on. So we are capturing the sequence and we are trying to define the probability distribution of the text. So earlier researchers have started by defining a probability distribution function, come up with a probability distribution function, and then train over it. Those models comes under the explicit density estimation category. So we are coming up with a function and we are trying to learn over it. How many of you understood? What's the idea? So we want to learn the probability distribution. How? Let's start with defining a function and then we can learn over it. This is how all the models that comes under the explicit density estimation category have been proposed. So just to give you an intuition, so we have two categories: explicit density estimation and implicit density estimation. In explicit density estimation, we'll define a function and we'll learn over it. In an implicit density estimation, we do not define a function because there are n number of reasons that we are going to see, and we cannot come up with a function and we cannot learn over it. So then, why not let model implicitly learn the probability distribution? We are not defining it, and the overall objective of our is to get the new data. So how the model is learning the distribution, let's not go into it. Let model learn it, and we just want the sample. So that all those models comes under the second category called implicit density estimation. It is clear? Okay. So there, from the taxonomy of all the generative models that we have, in explicit density estimation, where you have other two categories: traceable density estimation and untraceable density estimation. In both the cases, we are trying to define a function and then we are trying to learn over it. And some models are there, like neural auto density estimation, mass auto density estimation, pixel RNN, pixel CNN. These are all models define a function and then learn over it. In approximate density estimation, you have one of the model called variational autoencoder that you might have seen in one of the previous lectures, which comes under approximate density estimation due to some because you cannot come up with a traceable density estimation function. So, and in implicit density estimation, where you do not define a function and do not learn over it, you just come up with a model that somehow means using some technique, it learns over the data and you can generate a new sample. And one of the model is GAN that you have seen, and we are going to cover it again today in this session. So, any question at this point of time? So, what is generative AI? We got the intuition and the definition. We want to learn the distribution of the data somehow, and we want to generate new samples. Yes.
What I have learned about Markov chain model and virtual machine that comes in reinforcement.
Yes.
Okay. So are we saying that we are using reinforcement learning concept to develop this?
So Markov chain, there are some assumptions that we take. So independency amongst the chains. So we take only some of the previous contents instead of taking the whole content. So those assumptions, because we take those assumptions because the computational complexity of computing whole distribution is not possible. So that comes under that. So depends on how it is implemented. It may be a reward-based approach in case of reinforcement learning. You are considering any other approach.
That is a part of reinforcement learning, but that is not complete
Generative AI, yes.
because that needs
defining those functions and using the assumptions from there, then you can think of those approaches have been used, but not completely they are the generative AI. Similar to autoencoder model, which is not a generative AI framework model, but you use the concept of autoencoders and some intuition in the variational autoencoder, where you have two models, encoder and decoder. Encoder encodes image or any data into some smaller compact representation. However, that is not a generative AI model, because the vector that you come up from the encoder is a unique representation of that particular image. So you cannot generate new data out of it vector. That again, that will give you the same image. However, the similar concept have been used in variational autoencoder, where you have encoder and decoder architecture. Instead of learning a discrete vector, you try to learn the continuous latent space. So the intuition, if you have from Markov chain and the reinforcement learning, then it comes under this. So in explicit density estimation, we try to define a function. Just to give you a brief intuition of some of the models, like pixel RNN or pixel CNN, how they work. So you first define the function. So let's say likelihood of an image, distribution of an image will be product of probabilities of all the pixels value given the previous pixel. Now there are two questions. One is what you consider as a previous pixel. In which pixels we are going to consider. So we need to define some ordering. Assuming you take ordering from top left to bottom right. So for this pixel there is no previous pixel. So for this pixel, this will be the previous pixel. So there are two things. One is, and obviously this have a product of all the conditional probabilities of the pixels. So this is a complex distribution. So we cannot just learn over the data by simple distribution, probability distribution. So we are going to learn using a neural network. So there are two things we are going to use the neural network. And the second thing is we are defining it by conditional probability and product of all the over the pixels values. Then we need ordering. So we come up with some ordering. So we initially define. So this is the intuition of. So we need some ordering of the previous pixels. And once you come up with the function, and once you define the ordering of the pixels, then you can train over it. Train over the training data. So this is how some pixel RNN works. So the pixel RNN uses recurrent neural network architecture, which is again a neural network based architecture. So you start from corner, and then you try to learn over the image. You train over the image using some ordering. And once it is trained over all the data, then you can generate pixel by pixel. So you can generate one pixel and then the second pixel and so on in a sequential manner. So this is the intuition of pixel RNN. The problem is training we are doing in a sequential way, and generating we are also doing in a sequential way. That's why pixel RNN is slow. Then there is an improvement where convolution neural network have been used. Again, though simply convolution neural network is not a generative model, the pixel CNN is a generative model, where instead of using RNN, you are using now CNN model. And in CNN model, you use a convolution, a kernel, to move over the image. So now the idea of ordering the pixels, we are going to take those pixels as the previous pixels which are inside the kernel. That's how we are going to learn over the pixel CNN. So then we train over the image. However, the generation is still pixel by pixel. We generate one pixel at a time and so on. So in both the cases, there are two things we have to remember. One, then we have come up with a function. We have defined the ordering of the pixel value because we are working on the images, and then we trying to learn over the training data. What about text? So how we are going to learn over the text? Yes. So let's define break down into tokens and learn the composite probabilities and joint probability over the tokens instead of pixels. And we are going to use, there are various mathematical models we are going to cover in the LLM in the next session, either today or in the tomorrow. How LLMs works to generate the learn over the distribution of the data of text. So till this point of time, it is clear. Now the problem is again. So in pixel CNN also the problem is the sequential generation is a problem. Again, it is a slow. So some pros and cons of it. So pros, we can explicitly come up with the likelihood of an image because we are defining a function. And however, the problem is sequential generation. We are generating pixel by pixel. The another model that have been covered yesterday called variational autoencoder. That that have two networks called encoder and decoder. Right? So encoder encodes an image. Normally in the autoencoder, you have a encoder network. You give an input. It generates a compact representation in form of a vector. This vector is nothing but a numerical values. You can think of these numerical values as some properties of that image. For example, an image of a person is there. That vectors values might be representing, let's say, color tone, eye size, and so on. So hypothetically, we are saying this each value is representing some properties or features of that image, and now we have a compact representation of that image. And what we do, we give it to decoder module, and decoder module try to come up with the same image. And unlike other models that you have seen in the deep learning or machine learning, how we train any model, we define a loss function. We define a loss function and we try to optimize over it. Right? So in all the models, how we define the loss function? Let's say if you have a supervised learning problem, the predicted output and the actual output, and you define a loss function over it. And using some backpropagation mechanism, using gradient descent or any other variation of gradient descent, like eta delta, eta grade, and other optimizers, you try to minimize the loss. Unlike this concept, autoencoder, instead of having y to define a loss function, you use the reconstructed image. So reconstructed data, so you define over the x only. So difference between the predicted image and the actual image, the loss is defined, and the loss could be a root mean square loss or any other loss, and then you train over it. And now the model that you have to encoder and decoder, this could be anything. It could be a simple neural network having some input layer and hidden layer and one output layer, or it could be a CNN model, it could be an RNN model, depending on the task you are doing, and similarly decoder also. So you can think of it as a wrapper network which have two networks, which could be any other model which you have studied, So unlike training is done, and once the model is trained, the whole model is trained, you can use it for any purpose. For example, let's say I'm trying to build a model that can classify into cat or dog. So what you can do, you can just drop the decoder, because we have done the training, we have learned over the, and once the training is done, what it is mean by training is done, then this vector, which is a compact representation of image, now it represents that image, because we got the same image again. So you can think of this vector as a uh, in a in a latent space, one of the point, and the dimension of this space is the dimension of this vector, and that point represent that particular image. So we got a compact representation. What you can do, you can pass this to some classifier, you can put a sigmoid layer, sigmoid function, or simply a support vector machine, decision tree, or any other model which can classify into two categories, cat or dog. This is the idea of discriminative model of autoencoder. But the problem is, this cannot be directly used for generative AI. Why? Because this is uniquely representing this image. It cannot generate new image. So what we want, instead of coming up with a latent vector, we want to come up with a latent space out of which we can sample it. This was the intuition on which you have the model called variation autoencode that you have already seen. So, and there are some, why it comes under the approximate density estimation category, because learning over it, given the conditional based on the latent space over the z, the sample that we get from the latent space, the computation of this is intraceable. So we cannot compute directly this function. So we approximate it. So we somehow try to map it to a simpler distribution, let's say normal distribution with mean and standard deviation. That's why it is called approximate density estimation model, because computation of this is difficult. And you might have seen this in the previous session, how variation autoencoder works, how it learns the latent space, and then you take one sample and you give it to decoder, and decoder generates a new image. So instead of learning one single value, for each feature you learn mean and standard deviation for each feature. And for each feature, if you learn this, you can just pick one sample out of it, and you can vary the value of, let's say, smile, color, tone, and that will come up with a new image. So this is an informal idea of explicit density estimation model, where you define a function and you learn over it and you generate a new data. So till this point of time, is it clear? Any question? We're good to go? Fine? Okay. So since it is difficult to come up with a function and difficult to learn over a training data, why not just forget about defining a function? Why not just come up with a model that we give the data and somehow it learns, and the model can generate a new data out of it, which looks similar to the training data. Similar means the same distribution that training data has. So that's where so why not we just give up on explicit model densities and just want a model to have an ability to generate a new data. That's where one model comes, which is called generative adversarial network. So till this point of time, we are Now we are moving to second category, and we are not going to define a function. We are coming up with an alternative approach that somehow will generate new sample data, which is similar to the training data. That's where GAN, generative adversarial network, comes into the scene. Now there are different. So if we just see the acronym of GAN, there's one important thing is, so we need a network, neural network based architecture. Why? Because we want to learn the complex distribution. There's another term called adversarial. Adversarial means now we do not have single model. What we are going to do, we are going to have a model with two networks, and they are having an adversarial setting. Adversarial setting means they are competing with each other. Yeah, you can think of a game, of two-player game, where each model is competing with another. So, and obviously generative, because we want to generate a new data. So there are two models. So there are two things. Adversarial setting means we have two players competing with each other. So we have two networks, generator and discriminator. And unlike other machine learning or deep learning models where you have a model and then you fed the data and you define the loss function and you backpropagate it, you train it. Here we have, you can think of GAN as a wrapper network. So you can define generator as a CNN model or neural network or RNN or any other model. You can pick it as a generator. So you can define a generator as any other deep learning model that you have, and there is a discriminator model again that could be a neural network based model. So it's a wrapper network. It's not a different network. You are different deep learning model. You are using those different deep learning models as a generator or as a discriminator. We are having the setting as that they are going to play against each other. And depending on task, let's say if you are going to use GAN, though it is GAN is not popularly used for text generation, it is more used for the image generation. If somehow you are coming up with a GAN model for text generation, then you can use generator network as an RNN or LSTM or any other sequence model. If you are using images, then you can use CNN model or any variant of CNN model or any pre-trained network as a generator model. So the two networks are going to play against each other. Yes.
So the discriminator will always be an active neural network, or it can also change.
It can also change. So somehow, let's say discriminator is going to take two images. One is real and one is fake generated by the generator that discussed yesterday. So you might need a compact representation of it. So you can have a convolution, Boolean convolution operation. So you can have a CNN network, and then towards the end you can have a classifier to divide into two categories. So depend on the task. If it is a let's say sequence modeling, then discriminator could be an LSTM model, which is coming up with a vector context vector representation and then dividing into categories whether fake or real. So it depends on the task. It's a wrapper network, you can use it. The idea of discriminator is so there are two players, generator and discriminator. Generator, and they are competing with each other. Means generator wants to fool the discriminator. Generator will generate a sample, and discriminator will try to identify whether whether particular sample is generated by the generator or it is a real sample. So discriminator is nothing but doing a binary classification problem. So binary classification it is doing whether it is real or fake, and generator is coming up with that realistic sample data that discriminator cannot identify. So even discriminator takes two images or two data, one is real and one is fake. Discriminator cannot distinguish it whether it is a real or fake. That's how they are competing with each other, right? Also, let's say autoencoder model, unlike all the models that you study in deep learning and machine learning, what we give to the model? The sample, training sample, right? Here in GAN, we are not going to give any sample to the generator. So generator will try to come up with a sample based on some random data. So unlike all the traditional models that you have seen, we are not going to show the training sample to the generator. So what generator will take as an input? It could be a noise, a simple vector randomly initialized, and based on that vector, it is going to generate a data, generate an image or generate any data. So generator will take a random noise, could be simply a vector of some dimension, randomly initialized, and generator could be a neural network, simply a dense neural network or a CNN or RNN, anything, will generate some fake data, and discriminator will take this so discriminator have access to the real data, and discriminator takes some samples from real data and fake data, and it tries to identify whether it is a fake or real. Clear? This clear? This is an example. So random noise given to some neural network architecture that generates a fake sample, and again decoder, so discriminator takes a real sample and the fake sample, it tries to identify whether it is a fake or real. So this point of time we are clear about we are having two networks. One is generator, one is discriminator. Generator takes sample noise, random noise, could be a vector of any dimension, let's say 100 or 200 or anything, and it tries to come up with a output, a sample, a fake sample, or we are calling it fake, but it is a generated sample of an equal dimension having the training data, so that dimensions are same and the images are same, and discriminator takes a real sample and the fake sample and compare it. It just try to discriminate whether it is a fake or real. Clear? Okay. So we have a adversarial setting. Now how we train it? So you can think of generator is the network that is inside the generator is trying to learn some distribution over the image. So trying to come up with a distribution, probability distribution, and that you can represent, let's say, probability distribution of and out of it one sample is generated by the generator, and that sample is given to discriminator, and real sample is given to discriminator, and discriminator differentiate whether it is a real. This is the intuition of GAN. Now, so how training is done? Because now instead of having one network, we are having two networks. One is generator and one is discriminator. How we are going to train? So GAN uses alternative approach, because instead of just simply defining a loss function and backpropagating it through one single network, now we have two networks. So it uses alternative approach. For once it trains discriminator, and then alternatively it trains generator, and so on. So it do not train both the networks simultaneously. It trains discriminator, then generator, then discriminator, then generator, and so on. Alternative approach. So for once we lock the generator, locking means we are freezing the weights. So we just taking some samples. Let's say some M samples we have taken, and some M real samples we have taken, and discriminator trying to distinguish whether it is a real or fake. Based on it, we define a function, loss function, and then we backpropagate, and we only update the parameters of discriminator. And once the training of discriminator is done, then we lock the discriminator and we train the generator.
When we start the training process, would we train the discriminator first or the generator?
Okay, so the usual in practice, from an implementation side, we train first discriminator and then the generator.
So, but if we are training the discriminator first, we need some fake samples, but the generator has not started generating right now.
No, generator can start. I mean, it might be generating some noise as well.
Okay. So we generate the samples and then start training the discriminator.
Yes. So basically, what do you mean by training of generator? Generator means we are trying to update the weights. Initially, the weights that are there, you can think of it as an updated weight. So whatever it will give you as an output, you can think of it as a sample. It could be a simply noise, distorted image, or anything. So now this, you might have seen this value function. So instead of defining a loss function, we have a value function because we are having two players. So we are defining a value function that generator wants to minimize and discriminator wants to maximize. So how this value function comes? So if you see this equation, though it looks quite complex, it is basically nothing but comes from binary cross entropy loss. How many of you know about cross entropy loss? Binary cross entropy loss. So when you have a classification column, you can define loss function as a binary cross entropy loss. Simple idea of it. So loss is nothing but, you might have seen y log of y predicted plus 1 minus y log of 1 minus y prediction. Okay. And obviously you have n number of samples for the training, then you sum over it, and you have a minus sign also. So this is the loss function, binary cross entropy loss function. Do you know about it? So if you don't know, this is the loss function that we use for classification purpose. So how this? So it might look trivial. If you see here, it is quite easy to understand. So discriminator is there. Let's say we are saying real sample when y is equal to 1, fake sample when y is equal to 0. So let's say if y is equal to 1, then forget about this minus and the summation. We are taking only one sample. Then if y is equal to 1, then the output, so this will be 1 and log of y predicted. Y predicted, what was the prediction? That it is a real. Real means the output of discriminator was x. So this d of x representing the output of discriminator. And in case of y is equal to 0, so this will be 0. This will be log of 1 minus d of g of z. So g of z, so z was the vector, random vector. G of z, we are saying it is the output of the generator, and discriminator is generating the output of the generator as an output. So log of this. If you just add these two equations, log d of x, log 1 minus d of g of z, and now instead of having one sample, you are going to have n number of samples. So you might define expectation over it. So for one sample, it could be simply log of d of x plus log of 1 minus d of 0. And if you have discrete data, then expectation will be calculated as a summation. If you have a numerical data, it will be calculated as an integration. So we are just defining an expectation like. So now basically this value function is simply coming from the binary cross entropy. Now generator will try to minimize it, and discriminator wants to maximize it. So if you cannot understand it, let me just simplify it, this whole training loop. You might have been covered gradient descent in one of the lecture, where new weight is equal to old weight minus some learning rate multiply with the gradient over the loss function with respect to that weight. Simplified equation. You define a loss function, you calculate the gradient, simple partial derivative, calculate the gradient, multiply with the learning rate, subtract from the old weight value, and you get a updated weight. Okay? So training means you have to calculate the gradient. So we are going to calculate gradient here over the value function. So it is also represented by delta, and theta of d means parameters of discriminator, and theta of g means parameters of generator. So for that value function over the n samples, you are calculating the gradient, and once you calculate the gradient, you can update the weights using that equation. Similarly for generator, now in generator you can see this is not there. Why? Because there is no value, so it will be 0. Gradient, if you calculate the partial derivative, it will be 0. You are just calculating the gradient over it. So this is how you calculate the gradient. Now how the whole thing works. For training it, from the implementation side, it has been observed that you update discriminator k times and generator 1 time. So for all the training iterations, yes. Okay, for all the training iterations, for k steps, so what we are going to do, k times we are going to update the discriminator. We sample some of the samples from the generator, and we get some real samples from the original samples, and we update the discriminator by calculating the gradient. And once we update k times discriminator, we update 1 time generator. So this is that algorithm. In simplistic term, it works. So how many of you understood this till this point of time? So you got the idea of from generative AI to explicit density estimation to implicit density estimation, then how GAN, in intuitive way, how GAN works. Mathematical formulas I have already discussed by sir yesterday. I'm just giving you the intuition about it, how it works. Right? Clear? This point of time it is clear? Okay. So, but the problem is, so you might have seen all the models basically uses gradient descent or any other optimization techniques to update the weight. And in machine learning and deep learning, so this gradient descent or variation of gradient descent like stochastic gradient descent or any other approaches that iteratively update the weights actually designed for one network, not for adversarial setting. Adversarial setting matlab we have two networks which are competing with each other as a player. So normal gradient descent is not actually designed for this one. Though we are going to use gradient descent for updating the weight. So sometimes when you are training the network, it might not converge. So might not converge means so to generate a sample, you're not getting the good results because weights are not updated correctly. You're not coming up with the optimal minimum, optimal value for this. So generator is stochastic gradient descent or gradient descent. Other variation of gradient descents are not actually designed for this adversarial setup. Sometime when you train it, you might get some error. It might not converge. Also, there are another problem like mode call. So that calls one problem calls non-convergence. Another problem called mode collapse. So suppose you have a diverse data in the samples. Diverse data means you have samples of, let's say, images of cat, dog, horse, and so on. So you have, let's say, 5 categories of data. And once the model is trained, so you might see it is only generating image of cat or image of cat and dog. It is not covering the diverse data that it has seen. That is called the mode collapse rule. So it is not generating diverse set of samples from all categories. It might be generating from single category or might not be generating at all. So there are some variation of it of GAN that solve these problems. So at this point of time, we have covered how GAN works, how in an intuition way what is GAN, how GAN works, what are generators and discriminators, and how it is trained. So to give you idea in an implementation side, and you can map it theory with implementation. Let me show you one notebook of it. That will give you idea. Though some of you might not be familiar with Python, or so how many of you are not familiar with Python or machine learning? Implementation of machine learning using libraries. Okay. So I'll explain the code in a more intuitive way. What the point, what the cell is doing, and the syntax you can learn over it by looking at it and exploring it. But I'll show you what exactly what those cells are doing. So that will give you idea how intuitively how it is working. And then after the break, we are going to see some variations of GAN, which have been used for other purpose. And okay. And in the practical session at 4:30, one of the Mayank will show you some of the implementation point. You can just edit the notebooks and work with the custom data. So here we are taking a small sample data MNIST, which is available as a sample data from the libraries of the Python. Though if you want to work on a custom data, let's say you want to take some other images, how you can use that notebook and how you can work on train a GAN or over a sample images, other from the available data set. That Mayank will show you. So this is, if you can see it, let me. Okay, so is it visible? So okay, let me. Okay. Now I think it is fine. So before explaining the code, so there are some libraries in Python. One is PyTorch, one is Keras. So there are two alternative ways to develop any deep learning model. Either you can use Keras library or you can use PyTorch. Both are built on the top of TensorFlow. TensorFlow library is built on the top of CUDA. So in all the deep learning models, basically we are doing the algebraic operation behind the scene. Algebraic operations means matrix to matrix operation, matrix to vector, vector to vector. All those operations, why deep learning libraries we used and GPU we use to make the process faster. So to make the computation in parallel. For that, you have a CUDA library behind the scene that maps your code into CUDA familiar code, and that can run on the GPU. Now, writing your code in CUDA is difficult. So you have a abstract layer of programming style called TensorFlow. TensorFlow somehow make it convenient to map your code to CUDA layer, CUDA specific code. Now, on the top of it, TensorFlow, you have two variation of libraries called Keras and the PyTorch. So you can write your code in PyTorch, you can write your code in Keras. Normally, when from the learning purpose, when you are trying to build an AI or deep learning models, and you are not familiar with those complex terminologies, complex language concepts like object-oriented programming and those concepts in Python language, Python libraries, then you prefer you go with Keras, which is easier to write the code compared to PyTorch. Normally, PyTorch is used in the industries where you define a scalable deep learning models where you can define classes and so on, and based on that you can work on it. So normally in industries we use PyTorch. Normally, as educational purpose we use Keras. So both, however, in both the cases you have different libraries to work upon it, directly importing it and use it for the implementation purpose. This particular example shows the example using PyTorch. So there are different section of facilities available in PyTorch, like how you load the data and what are the modules to load the data, and how you split the data, how you normalize the data, and how you build a model and how you train over it, what are the predefined functions are there. So that are available in PyTorch and as well as in Keras. So you can, those if you, even if you don't know about the Python language, but still if you have some concept of programming, so basically what is function, how you call a function, how that returns a value, how you can see the dimension of the functions, dimension of the output of functions. So then you can work with those libraries as well. So just a quick tutorial is given here. I'll share this notebook. So you just visit this website. So you can, that gives an idea about PyTorch. So you can see here, quick start, what is tensors, how datasets, what are the datasets available as a sample datasets, and how you can use the data loader library module to import the data, and how you transform the data, and how you build the model, and how you optimize it. So there are some samples, and it is showing here what how it works. So you can just read about it if you do not have any exposure to a PyTorch module library. So this, let me just give you intuition. So this, here we are from Torch Vision module. We are importing some modules called datasets because we are going to take a sample dataset instead of we are providing a dataset, which is one of the dataset called MNIST. If you know about MNIST, it has handwritten digit data of 0 to 9, and transform modules. Basically, you want to transform your data into some other form, like pixel values you want to normalize in some range, or you want to change the mean, or you want to change scale it. Then there is a transform module. So here we are importing some necessary libraries. This, what we are doing, we are first, so we are defining a transform which will transform the data first into tensors so that it can be run on the GPU. We are normalizing the whole data into -1 into 1 by taking mean and standard deviation 0.5, 0.5, because generator that is going to generate an output, it is will be giving in we are going to use activation function like 10h, so it will give you output in between -1 to 1. So we are just transforming it, normalizing it. So this we are defining the transform, how it is going to transform. This MNIST data set we are taking a sample and train we have put it as a true because we are going to train over it the data. Download is true. Transform we have defined transform so that MNIST data will be transformed using those parameters that you have given. We using the data loader module, we are loading the data, and the data loader module, what it does, it categorizes your data into folders, directory structures. So for example, the handwritten digits, so 0 wali image will go to the folder called 0, labeled as a 0, 1 will go to the folder as a label, and on the top it is going to the directory called data.
So this data loader will automatically do that.
That automatically do. So, and you can use that data loader on the customer data as well. So MNIST train data batch size we have defined 25. So all the data is divided into batch of 25, and we are doing it shuffle. True means the batch we are picking up from the data. First, it will shuffle the data and then pick the 25 instances from the data. So, though if you go one by one, you can understand what it is doing. Let me just give you the broad idea. So here we have loaded the data, right? Here we are visualizing the data. So we are visualizing some 16 letters. So this is just for the plotting the data. So for batches in train loader, so in train loader we have the batches of the data in 25 size. We are breaking it, so we are only showing one batch of 16. Now here we are defining the generator and the discriminator. So let me give you just a simple intuition of it. Generator model is a sequential model, takes an input, pass it to second layer, then third layer, and so on. Initially it is taking some random noise of dimension defined by the latent dimension, which we can define it as a parameter that will give you output into 4 into 7 cross 7. So 7 cross 7 matrix, 4 is the channels. Whenever we define a function, even a simple neural network, we combine the input and we use the activation function for the non-linearity. So we are using ReLU. Then we are unflattening the output. We are doing it as a 4. So here actually the linear layer is taking generating output of 4 into 7 into 7 means how much? So any number is there. So it is a single vector. In the vector we want at the end from the generator what we want? We want image. So we are making it multidimensional with 4 channels and 7 cross 7 matrices. Then we are upsampling is the factor 2. We are basically the 7 cross 7 image will be converted to 14 cross 14. And we are defining a convolution layer which maps from 4 channels to 8 channels, and we are using kernel size 3. So 3 cross 3 convolution will work. Padding 1 is taken so that the output will be the same size. So your output will be 4 into 8 cross 8. So this is and in this, and we have repeated it again. We have scale up with the factor 2, so that 8 cross 8 it will become 16 cross 16. And from this layer of input, you were getting 8 channels. So here from 8 to you are scaling up to 16 channels. So 16 channels means you can think of it as a okay. So what was the output of last? 7 cross 7 to 14 cross 14. Okay, so you can think of in the previous here you have 4 matrices of 7 cross 7, which you have 14 cross 14 when you upscale. So here you have 8 into 16 matrices of size 14 to 28 into 28, which is the size of basically MNIST data one image is of 28 into 28. So now we have how many matrices behind the scene? 8. So that layer, what is it doing? So that doing from 8 to 16 channels, and here what we are doing, we are 16 to we are bringing it to 1, keeping the size same, which is 28 into 28. So now at the end, generator will give you a 1. So, and we are performing a 10H activation function to give the value -1 to 1, which is similar to the transform that we have done. And we define a forward function. When we pass a latent vector into the model, it will return the image of 28 cross 28. So this is how generator was defined. Similarly, you have defined a discriminator. So discriminator performing some operations, and towards the end, all the output was flattened, and it is giving from 64 into 4 cross 4 into 1. So you are getting output only one value. And we are not normalizing it to the activation function. Last layer we have not used any activation. So it will give you some real value, some numerical value it is giving. So this is discriminator how it is doing. And that real value in this particular example, if it is larger in size and negative, it is fake, it is in positive, it is higher than it is real. We are not squashing it in between 0 to 1. It is just we are taking a simple raw value. Okay, that also defines the function. So we have loaded the data, we have defined the generator and discriminator. We have only defined it, we have not used it. Okay, so after defining, this initializes model and their optimizers, that which optimizer we are going to use. So by calling that class, so if you know some concept from object-oriented programming, when we define a class, it is not actually working. We define an object using calling the constructor. So here we are calling the constructor, we are passing it dimension of latent space. This basically lines, you can avoid it, you can just remove it. While you are writing, if you have a system, laptop, or any infrastructure which has GPUs, so that basically transforming the data into model into GPU so that it can work faster. So you define the generator object, discriminator object, you define the optimizers, that you are using the Adam optimizer, which is again a variant of gradient descent, and this defines the training loop. So if you map with a theory, here number of iterations are 5, and for epoch in range, number of epochs, for each epoch we are training discriminator 5 times. So we are training the discriminator, we are taking some fake images, and we are defining the discriminator loss function, and we are back propagating it. So all this backward function, it is all coming from PyTorch. So you are not implementing from the scratch, they are there. And similarly, we are training the generator for only once. This particular line of code, basically the output, when you train it, it shows the output, the loss value and generator loss, discriminator loss for each epoch. We are not going to see for each sample, we are going to see for each batch size of 250. So once 250 samples are completed, then it will show the output. So let me quickly run it. First you have to run it. So there, if how many of you are comfortable with Google Colab? So how many of you seen that Google Colab? So okay, so there are GPUs and TPUs are available. So if you have a model that requires GPU, then you can connect to any GPU. Here we are connecting to T4. It is connected. So if you just run it, so that So mainly the notebook on which you are going to work, mainly instead of using MNIST dataset, how you are going to use the custom dataset and how you are going to train the GAN model, you are going to see. This is completed. So okay, so we have defined it. So this the output. Now we define generator and discriminator. We are only defining it, so it is not taking much time. We are initialize the. Now we are training it. So and for each epoch it is showing some 16 images. So okay, so you can see it is only showing this line for 240 samples after 240 samples. So this particular basically logging of the output, we are doing it for this. And for first epoch it is going on, and once the first epoch will complete, this particular shows the output of the generator samples. So how the model is trained just for the checkpoint. And this is for the inferencing. Once it is trained for 5 epoch, it shows how we can generate some data. So you can see here, though image is not exactly as the MNIST dataset, because we have only used 5 epoch. If you train it for more epochs, you will get similar output as the training samples. So it is running, it will take time. So this is the idea of GAN. Then the variations of GAN or some other topic we'll go see in the next session. So I think we can take a break.
Yeah.
So any questions you can ask. So I thought you, so I think now you have understanding of how generative AI works and what are the various